Thank you for the kind introduction. Yes, so today I'll be talking about urban climate extremes, the changing pattern, and early warning. So I'll give you some ideas of what exactly we are doing. So when it comes to extremes, as we all know, an IPCC working group, one working group two, have been telling us that human-induced climate change is already happening. It's not a futuristic thing. It's actually happening now, and it's affecting different parts of globe. And there are evidences of observations like increase in heat waves, heavy precipitation, droughts, tropical cyclone, everything. So of course their attribution to human influence has left them still their fight. So now the thing is something like this. We know that climate change is affecting us. Now we are looking for some solution. So what do you support? And for a country like India, where adaptation we need to improve, we need to improve our adaptive capacity. We are lacking in terms of adaptive capacity. We means most of the population of our country. So then for that case we have to improve the adaptation, and any adaptation strategy which is for climate change, it should be founded based on the foundation of climate science. Otherwise this adaptation can be maladaptation. So what we need to do is that we need to think of adaptation, we need to think of climate services, but that should be based on solid climate science. So with this, I will just quickly go through a figure which we generate as a part of IPCC Assessment Report 6 Working Group 1, where we tried to understand that how human influence has actually impacted heavy precipitation. So I think the IPCC Assessment Report 6 chapter, where I was one of the legal planners responsible for the part heavy precipitation. So if you have time, please go through IPCC. Many things. There are few things which are very important in this report. One of them says that urbanization plays a role. So the first time IPCC has very clearly said that there is confidence that urbanization lead to increase in extreme precipitation, which is very important. The second thing also IPCC said is that the second thing IPCC AR7 is coming, well, one of the major thing is that city and climate change. So it shows that cities are mostly affected because of climate change, because high population, high infrastructure, and so on. Now, if you look into the precipitation and human influence, so we are sure that heavy precipitation has increased. So this is they represent the globe in terms of this kind of hexagons, and the South Asian region where India is located, and you can see we say that there has been increase in extreme precipitation, but there is confidence that it can be attributed to human contribution. This is because of limited agreement. Why limited agreement is coming? Because first thing is that models are not very good for precipitation, so there is a huge uncertainty. The second part is that there are a lot of local changes which also affects the precipitation, extreme precipitation specifically, and quantifying them is one of the major challenges. And urbanization is one such thing. So now I will go back to one of the very famous paper which was published in 2006 by Professor B.N. Goswami, which first said that extreme precipitation in India is increasing, and what they have done is that they have picked up a box over the central India, and when they plotted the trend, what they have found is that very extreme rainfall, that means where the rainfall amount is greater than 150 mm per day, that two occurrences have increased, and also greater than 100 mm has increased, whereas medium rainfall, which is 5 to 100, they have actually reduced. So, and uh, they said that essentially the extreme precipitation have increased. So after that, what we started, we wanted to see that okay, extreme precipitation have increased, that is fine. But let us try to understand that if the spatial variations of extreme precipitation has increased or not. And what we have found is that if you are going at a local scale, you will get a mixed kind of change. Somewhere it's increasing, somewhere it's decreasing. So increasing points are higher in terms of numbers, and there is huge spatial variability. So one of the things we started hypothesizing is that the increase in extreme precipitation. So if you look at the spatial variation of trends, that has increased quite significantly. You can see that from 1950 the spatial variation of trends have increased quite significantly. What does it mean? It means that the changing pattern of one region is becoming very different from the changing pattern of other region. And that shows that if it is because of just global change, then all of them will have very similar kind of trend. But when local factors starts playing into it, then you will get these variations, this spatial variation, and this is increasing. That clearly shows that probably our uh, spatial, probably some of the local changes are actually playing a major role. So we published this one in Nature Climate Change long back in 2012, and then one of our student people started working on something else. So what he tried to do is that he tried to find out before 1950 the changes and after 1950 the changes. And this is some sort of a distribution. Before 1950, you can see that 46% of the stations are showing increasing trend in India, 30% decreasing, and 21% no trend. And after 1950, 46 has become 47, 33 has become 30, 21, 20. Not much of change. But grid-wise, there has been a lot of dissimilarity. You can see that 75% of the grids have no similarity. That means increasing has changed to decreasing, or decreasing has changed to increasing, and so on and so forth. So there has been a reversal of trend at many occasions after 1950. So you can see before 1950 increasing, among before 1950 increasing, only 45% are continuing to be increasing. Similarly, before 1950 decreasing, only 49% are continuing to be decreasing, and something like this. So it really shows that there has been a lot of change in terms of trends. Then what we try to do, we try to use all the change point analysis where we are trying to understand where the trend has changed, with which year. And try to understand if it is if the change point year is in between 1900 to 1925 or 1950 to 1950 or 1950 to 1975 or in between 1975 to 2000. We are trying to understand where it is happening. And what we have found is very interesting. We found that the regions with high population and when there are some built-up region, if you consider only those risks, what we are finding is that 51% of the change points, that means 51% of the grids are having change points after 1975. Now 1975 is something after which we are seeing extensive urbanization in this country. And you can see that highly populated regions or urban regions are showing, most of the grids are showing change point after 1975. But if you are considering non-urban regions, you can see it's well mixed. So that clearly shows that it is one of the GRE paper where you started saying that look, urbanization is actually playing a major role. Most of the urbanized regions are showing change point after urbanization. So at that, then we have come to very specific questions. Let us look at all India and find out urban regions are getting any specific kind of changes or not. So this was done again long back 2015 by one of our students. What she is trying to do, she is trying to pick up some of the urban regions and consider the 100-kilometer radius and outside region, and she is trying to understand if there is a change in the trends. And what she has found is something interesting. So let us pick up this plot. This is all India, and this dotted line shows the percentage of increasement and percentage of urban regions. Now, if you consider this increasing trend points, among these increasing trend points, how many are urbanized regions? Among decreasing trend points, how many are urbanized regions? And when she looked at it, what she found is that if you consider the southern zone and the western zone, these are the regions where you can see that post 1950 you can see very strong urban signature, because this one is crossing the dotted line. That is, the increasing trend urban fraction is more than the normal urban fraction. That clearly shows that urbanization is playing major role. To make it more clear, what we did is that we divided the time period into two parts, 1951 to 1978 and 1979 to 2007. And when we did this, now look at it very carefully. Now you can see that increasing trend points are actually crossing this dotted line because of urban. That shows they are because of urban signature. And very prominent in this report is 1979 to 2007. There is a near past graph. This is the long past and this is the near past. In the near past, you can see that every region, the urban signature is becoming very, very important, and that clearly shows that urbanization is playing a major role in terms of increasing the extreme precipitation. Now, of course, the question now comes is that how does urbanization affect extreme precipitation, or how does it result into increase in extreme precipitation? So there are specifically 4 ways by which you can think of urbanization may result into increase in extreme precipitation. The first one is that urban heating. So, we all know that urban regions have higher temperature, and when you have higher temperature, the air has more moisture holding capacity. With per degree increase in the temperature, the moisture holding capacity increases by 7%, and this is by the Clausius-Clapeyron theory. So Clausius-Clapeyron thermodynamic theory says that. Now urban regions have more moisture, so when it comes in terms of extreme precipitation, this is getting reflected. We all know that Clausius-Clapeyron is only reflected in terms of extreme precipitation. So you will expect that urban regions will have more extreme precipitation. The second thing is that urban heat island effect. That means urban regions are having higher temperature compared to the nearby non-urban region, and because of which there will be a differential heating, and there is a differential heating that results into more circulation towards urban regions, that results into more rainfall. Reason is urban regions generate more pollutants. So essentially pollution is more, so the aerosols are more, and aerosols are cloud condensation nuclei. So they help in formation of cloud, and when they help in formation of cloud, that results into more extreme precipitation. And the fourth one is because of urban structures. So how does it happen? So for example, let's say in urban regions there are a lot of built-up regions, high-rise buildings, slums, low-rise buildings, and so on and so forth, roads. So what happens if we assume that there is nothing in an urban region, there is a huge wind that is coming, they have the full cross-section over the urban regions to flow. But when the structures, the wind flow gets restricted, and so the cross-section area gets restricted, so the velocity increases, that results into more eddy generation because there are building corners and everything. And when there is more eddy formation, more instability, and in more instability means more cloud formation and more rain. So urban structures also result into increase in extreme precipitation at certain pockets in the urban region. So we wanted to do some kind of statistical hypothesis testing to try to understand that if urban regions urbanization really result into extreme precipitation. So what we did, we have picked up 2 regions. One Mumbai, of course, highly urbanized region, and the second one is Alibag, which is exactly at a very similar geographical region, very close to Mumbai, but it is a town sort of thing, so it's not an urban region. So we wanted to see that if we consider Mumbai and Alibag, do they show similar kind of extreme precipitation change or different? If they are different, then that shows that urbanization is playing a role in Mumbai. So what we did, we have the data for both Mumbai and Alibag from 1969 to 2008. So what we considered, we divided the data into 2 parts. One is 1969 to 1988, and the second one is 1989 to 2008. Of course, 1989 to 2008 is considered to be more urbanized compared to the first half. Now what we did, we performed the quantization. I'll tell you what exactly we have done. So if you look at Mumbai and Alibag here, and these are the large-scale circulation pattern. So this large-scale circulation pattern somehow results into wind circulation, and that results into extreme precipitation over here. Now, if there is no change, then this large-scale circulation pattern will result into some kind of rainfall. So that if you have observed rainfall and large-scale circulation pattern as a relationship, if they are same for Mumbai and Alibag, that means there is no impact on urbanization. So that's what we exactly tried to do. What we did here is that we took the reanalysis. Of course, we did some dimensionality reduction in principal component, did some clustering and so on. And finally, what we tried to do, we tried to understand if the circulation pattern that results into extreme precipitation under that class, if the relationship between rainfall and circulation pattern has been changed or not. And this is what we tried to do. So when we did that, we have found something interesting. First, what we have found is that there is one specific circulation pattern that results into precipitation over this Mumbai and Alibag region. This is cluster 1. Now, if you look at 1969 to 1988 and 1969 to, sorry, the second part. So if you consider them, if we find that there is a decrease, actually there is a decrease in cluster 1. So that means the large scale circulation pattern extreme precipitation has actually slightly reduced. Then what exactly is happening? Then when we checked in Mumbai and Alibag, we did some quantification where we are trying to understand, given a circulation pattern, what are the changes we are expecting in terms of extreme precipitation. This is what we are trying to find out. And when we are trying to find out what we are finding is that, let's say these are different quantiles and these are the values for cluster 1. And what we are finding is the first one is for 1969 to 1988 and second red one is 1980 to 2008. This is for Mumbai and this is for Alibag. We can ignore cluster 2, 3, 4 because they do not result into very high rainfall. So you can clearly see that in the recent half year for Mumbai, there has been a sudden increase in extreme precipitation. And if you look at Alibag, it's not happening. So that clearly shows that given the circulation pattern that results into extreme precipitation, because of urbanization, the more generation of extreme precipitation is happening over Mumbai compared to Alibag. Alibag it has reduced because circulation pattern has reduced. But in fact, there has been significant increase and that association has also changed because of urbanization. So that clearly shows that urbanization is resulting into extreme precipitation in Mumbai. Now, so the one of the major thing when you're talking about extreme precipitation in Mumbai, this urbanization also affects the spatial variability within the city, and this is quite well known. So if you remember, in 2005 there was an extreme precipitation in Mumbai. Santa Cruz on the station receives 900 mm of rain in just 24 hours, and 20 km away there is another station which receives only 80 mm of rain. 83 mm of rain. So that shows this sort of urbanization. And this urbanization is well known to the Mumbaikars who live in Mumbai. But what we wanted to understand is that what exactly is the reason behind such a huge spatial variability within the city. So what we did, we have done a very high resolution physics-based modeling with the help of weather research and forecasting model, which is essentially a dynamic downscaling model. So we consider the Indian region like this, and we have run the model at 3 km resolution, so high resolution. And in Mumbai also we have around 6 weather stations which are available set up by BMC to understand the spatial variability. Now we have considered 3 cases of simulations. One is we have not considered any urban canopy model. We have not considered urban radiation effect. That's it. As second one, we have considered a single layer urban canopy model. Urban layers are represented by just the same height of building. So the wind profile gets changed because of this. The third one we are considering multiple height buildings and so on, which is high resolution model. This is multi-layer urban canopy where these eddy formations are happening. So our purpose is to understand these eddy formations. Will they result into more extreme precipitation or not? So this is something what we did. So this is the observed rainfall on one of the extreme rainfall. If you do no urban canopy, we are unable to present. If you are doing singular urban canopy, it's likely but still not. But when you are doing multi-layer urban canopy, you can see that there is some matching which is happening. So this is the mean precipitation. This is no urban canopy. And single layer urban canopy, they are not matching, but when you are doing multi-layer urban canopy, it's matching. Except for this, for all other days, you can see that multi-layer urban canopy is quite well representing the Mumbai's rainfall. Now the second important part is the spatial variability. So we also plotted the spatial variability of Mumbai rainfall. So this is the spatial variability. As I told that the huge spatial variance across the stations, but if you do a no urban canopy or urban canopy, they cannot represent. But if you do multi-layer urban canopy, then you can reaching actually the spatial variability which is there in observed. So let us look at this, what exactly is happening. Let's focus on this figure, specifically this figure. Zoom in and focus on this figure. So you can look at it, you can find that this is essentially the observation. The blue line is the observation of the spatial variability. That means how different one station with respect to another station. Now, if you don't use any urban canopy model, it goes like this. If you use single layer urban canopy model, it goes like this. But when you are doing with multi-layer urban geography model, that means building structures and everything, then you can see it is producing high spatial variability, and this is happening simply because we are having these ADs which are forming, and that results into increase in spatial variability. So this is what I wanted to say is that if you look at Mumbai, the extreme rainfall pattern, you can see this is the region which is getting low rainfall, this is the region which is having high rainfall, and so on. This is one of the days, or no, this is the average annual maximum rainfall. Now when you are doing it with urban canopy, so this is what I wanted to say. Maybe I'll zoom in again and I'll try to show this part. So if there is no urban regions, you'll get extreme rainfall like this. But when there are urban regions, as I said, that there are few pockets which results into extreme high rainfall, and that results into a high tail, more spread distribution of rain, and that makes it really very challenging to model the urban extreme precipitation. And what we have found is that Shubham Paul did this work. If you go beyond 5 km, most of the cross correlation actions vanishes. That means urban regions have maximum decorrelation length of 5 km, which is again very critical and challenging. And then what we have found is that why is it happening? So we have taken a cross section, and in that cross section, what we have found is that it results into huge number of pockets. These are essentially instability pockets, and you can see that if you are using multi-layer urban canopy, there is a huge number of pockets, red to blue. That means huge difference is there, and that results into this is more than these columns. So that really shows that this kind of pockets results into more extreme precipitation at certain locations. Now we'll go more into the climate services. But before climate services part, we all know that urbanization results into further heat wave, extreme precipitation, flooding, etc., and so on. Now, if you look at IPCC, so till now I was talking about the science part, which is more on IPCC Group 1. Now we are talking more on IPCC Working Group 2, which has a high statement that says that in urban settings, observed climate change has caused impacts on human health, livelihood, and key infrastructure. And it says also observed impacts are concentrated among the economically and socially marginalized urban residents. That means informal settlements, which says that in urban regions, those who are essentially living in slum areas, which are more affected compared to those who are living in high-rise buildings. The third thing is that infrastructure, transportation, water, sanitation, energy system, everything has been compromised by extremes, which result in economic losses, disruption, services, and impacts to well-being. But if you look at the Indian literature is still restricted to urban precipitation or bit of urban flood modeling, but it does not really tell you how to really quantify. This kind of quantification and solution are still lacking in Indian literature. So, what are the need of the hour to make the urban smart, as a weather smart urban system? You need in urban region, as I said, that there is a huge spatial variability, so it needs an extensive monitoring and efficient information dissemination. You should have a very early warning system so that you can save people's lives, people's property, save people's time as well. And with hyper local information, you need to go at hyper local because it has very high spatial variability. And you need a specific decision support system so that you can actually take some of the no regret decisions, and then infrastructure planning and so on. The challenges is that modeling and monitoring of urban climate is very difficult. Lack of representation of urban and human component, and finally interdisciplinary approach for developing decision support system. We are still very much lacking. Not only India, most of the globe is actually lacking this area. So what we did is that very recently, one of the insurance company, HDFC Argo, approached us for developing some sort of a weather smart Mumbai city solution. So we worked on something known as weather smart and climate ready urban forecasting system or something like that. So one of the things I'd like to mention is that we know that Mumbai has been suffering because of flooding, but till 2021 there was no flood monitoring system. Even there is some flood monitoring system, but still the data is not available. So let's say on a monsoon day, which else in Mumbai. So if you have to go from one part to another part of the city, and if it is raining, you don't know if any regions are getting flooded or not. So that's not the challenging part. So what we thought is that since there is not, so can we develop some sort of a portal, some sort of a system which will be run by the Mumbai citizen for the citizens. So what we thought is that can we really improve the state of art weather system with some sort of a citizen science. And for that, what we thought is that we'll use the social media to do crowdsourcing as well as local people, local NGOs, and then we'll take satellite image and available videos in the smart data to get a real-time flood map. Then we'll use science modeling, which is regional modeling, then coastal modeling, and then finally we'll all of them together to develop a high-resolution urban flood modeling, which will give you the forecasting in one way, and the way it will generate flood and flood risk map, so that we can go for damage estimation. So this is what was our initial plan, and we started working, and we found that it is extremely challenging when you are really working on a operational real-life problem. It is very, I mean, it's quite easy to really develop some kind of a model and show some validation, but when it really needs for applications, it's a challenging task. So first thing what we looked at it is that we found that there is absolutely no data is available. So what we thought is that let's start collecting some data. So we started using Twitter, which is present now known as X. Started it was Twitter, which was free system. So we thought of first collecting data from Twitter. We started collecting data because we wanted to know that if you have to do crowdsourcing, you have to be very sure that crowdsourced data is reliable. So for that, we have talked to few volunteers who are actually well trained, and they are ready to give us some information, and we'll sort of getting word-wise information. So we trained the volunteer initially to get some information. We created a WhatsApp group. A lot of people were there, and then we sort of getting different information from different people, so that we can keep on updating and see what exactly is happening. So, and we found that this crowdsourced data has a huge, some sort of a information system. So, let us see. This is one of the days, July 5, 2022, where we have got tweet information like this. We can see this is the region where a lot of people are saying that many regions are getting waterlogged over this region. And when you have checked with the volunteers information, we found the same region where actually a lot of water information is coming. They are matching. Now, when they looked at the rainfall information on that specific day, we found that this is the region which receives very high rainfall. I'll come back to this, why this region is receiving very high rainfall. And this is the region where there is low elevation. So all of them are actually matching with each other. That shows that yes, this is the region which is very likely to get very heavy flooding, and it is actually saying the same thing. That clearly shows that whatever information we are getting through crowdsourcing, they are important and useful. Let us start using them. Once we have that, then we thought that what exactly let's happen from 2017 to 2022. So we wanted to understand what exactly happened. So from 2017 to 2022, when we are doing what we have found is that though the important tweets have increased, the useful tweets, but number of tweets have reduced related to extreme flooding. So that clearly shows probably BSC is doing something because of which the flood situation is improving, because they are for very similar kind of rainfall. So, but there could be another reason, because 2020, 2021 and 2022 is mostly flood COVID affected. So maybe people are not going out, so they are not doing. So for that part, what we did some ground survey. So we talked to different people and we realized that BMC has done a huge amount of work, the municipal corporation. And we found that the regions where actually it has worked, most of the regions, they work quite significantly. So what we did, we talked to the residents over that region who lived there and the shopkeepers who kept their shops open even during the COVID time. Totally. So we found that it really worked. So which was a good thing for us. We realized that tweets are really very useful information. So then what we thought is that then we go back to the rainfall. As I said that this is the region which receives very high rainfall. Why is it so? When we looked at it, what we have found is that what is the pattern? You can see there is a horseshoe pattern in the extreme rainfall over Mumbai. Why is it so? Then what we have found is that if you consider the elevation, this is the high elevation region, Sanjay Gandhi National Forest, and this is the low elevation region. So when moisture comes, there is some sort of orographic thing that is happening that results into heavy rainfall over this region. The heavy rainfall is happening over low elevation region. So that will result into flooding, and that's what Mumbai is. And then what we thought is that we have to understand the spatial variations of Mumbai rainfall. Let us first the clustering. First we clustered similar kind of stations under each class, so that each of the class we can do a good downscaling that can be representative of all other classes. That we did started using some AML approach. So what we did is that we have considered the observed rainfall, and then we have considered the global force model output, which is known as GFS output. And from GFS gives typically at 50 km resolution for NCEP from NCEP. So we took the NCEP GFS and then started downscaling it with a CNN method, convolutional neural network. So the idea was that can we really improve at a station level, at a very high station level we are trying to do. And what we have found is that for instance it's not working. So then what we use some method which is known as transfer learning. We took the same model but do a special training on the extreme days, which are limited number of days. And then what we're trying to do is that if GSS says extreme days, then we are using that transfer learned model or otherwise model. And then we check how is it working. This is done by one of the student Pooja Tripathi. And this is considering the original forecast system. If you consider the heat rate, how many times the extremes are correctly forecasted, you can see that with GFS the heat rate is quite low. When we are using CNN based downscaling with GFS, then they are improving. But as soon as you are using transfer learning based CNN, you can see the heat rate is as good as 80% in many locations. So it is significantly improving. Second thing is false alarm. How many times we produce extremes but it's not actually extremes. GFS has high false alarm, which is bad. CNN also has reduced little bit, but if you consider the combined model, which is a transfer learning model, it has reduced quite significantly. So that clearly shows that after doing a proper machine learning kind of thing, it is actually improving. Once we have this, then we thought that we are getting a lot of rainfall information. Now let us install some sensors. So two of our postdocs, Mayank Gupta and Aniket Nalka, so they have done a huge job of sensor installation, which is a very easy thing. Because when we are doing a sensor installation, we make sure that security TVs, everything is there, because we are putting it in one place and there may be vandalism, there may be something or other will happen. So what we did, and we also found the electricity and structural support. So we started talking to local people and multiple visits, talking to the engineers, take some feasibility study, getting NOC. If it works, then again go back and again talking to stakeholders. So it was a multiple iterations, and finally getting official permissions and then going for sensor installation. So it was a very difficult task, but they and they have installed a few sensors over this region. So our team has sensors to get the real. So it shows something like this. You can see lots of ups and downs is happening because under the sensor is side. So there will be some signal or something. But you can see when there is rainfall, it immediately shows that rainfall is happening. Things are getting waterlogged. So this is at Pakula Nala. This is another canal sensors. This is for Mithi River. You can see that the rainfall, how the things are actually increasing, water level is increasing. So that clearly shows, and this can be a very good validation data for the extreme flooding. With this, what we did is that our team has developed a Mumbai flood app, which is will be used for forecasting. So our plan is next. Since we'll make it 3 hourly rainfall forecast, but last year we have 3 rainfall forecasts with daily rainfall forecast. And so this was an Android app which is available, as well as there was a website which was available during the monsoon. Only keep it during monsoon, because non-monsoon there is no rain. So only during monsoon this website will be available, which will give you 3 days near real time hyperlocal rainfall forecast It will give local train information at railway station what exactly is happening. It will give you the water level wherever we have installed the sensors, and also it will also collect a lot of information from it, and it will keep on providing to the giving it to the people. And also at the same time, whenever people are giving their information, so that will be automatically updated. So essentially, a person who sees flooding is happening, they can give information through this app. Immediately, other people can see. So it is the way like citizen is actually helping citizen in terms of providing the real-time information. So Mumbaikars can report waterlogging through this app, and immediately it will be available. So this is some sort of a structure you can see here. So let's say this is one of the stations. Just a minute. Yeah, it should work now. So I know somehow it's not working. Give me a minute. Just give me a minute because this is important. I need to show this point, but sounds not working. Let me just. Yeah, no, that's fine. I have another video which I'll just show. Yeah, so I think I'm there. I'll just switch the sound and I'll show it. can you see this? Yeah. So this is one of the app which is being designed. Yeah. So essentially, you can see here. So these are essentially the stations. You can pick up any of the station. Let's say if you are picking up one of the station, what it will give you is that at present, what the last 12 hours, what was the rainfall value at every hour? Then what was the forecast for next 3 days, and how did it perform over the last 3 days? And one thing also we wanted to show is that how the model has performed over the entire season, because a person only believe this forecast if they will see that how did it perform over the last few days or the season. So this is what it actually gives. You can see hourly rainfall observations, 3-day rainfall forecast, and how did the model perform. Now this is something which is very important. It shows that let's say someone is finding his region is waterlogged. He has to give this information for others to use, and this is known as crowdsourcing and bringing citizen science. So let's say someone is giving current locations, giving his or urban height, and giving the waterlogging condition. Initially, go back again. So let's say someone there is a knee length of water, providing his or her own height. Then click on knee length of water, select the location, and making it okay. Immediately it will be visible on the web app, and others will be able to see. Now, this is the Android version which we have considered, and the Android version also you will be able to see exactly the same thing. Now, this is about the sensor data. So you can see that these are the sensor locations where you can actually click on the sensor locations, and as soon as you click on the sensor locations, you will see that on extreme day, for example, how the water level has increased over these regions. And these are of course the sensors. So this is all what we have done. Now I will go back to the presentation, and if you can see that for the last, yeah, hello, can you hear me? Yes. And when you looked at it, how did we perform? And this is showing because this year, the optional forecast of the government agencies have been highly criticized. But for this specific season, except just one extreme event, for all the extreme events, it performed very good, and it has been correctly forecast. For example, one of them on 20th July, where it received very high rainfall, and it has been forecasted correctly this extreme rainfall. The other one was 25th September, where there was extremely heavy rainfall, more than 200 mm rain in just few hours. And you can see that this was correctly forecasted where all other models failed. So that shows that this model is actually working quite well. And this is what we have done. So this is starting from 1st June to last day. So how did we perform? And as I said that we have missed one of the extremes. So this is one extreme that we missed completely. And other than that, for most of the extremes, we could forecasted correctly in this season. And this was available last season, all the Mumbai. Around 2 lakh people actually check this website. And at the same time, we are also doing some tweet analysis. We are immediately, every day we are providing with what sort of information people got about Mumbai floods, whoever was positive and whoever was negative, we did something. And also during the extreme rainfall, we showed what railway line is Mumbai's lifeline. So what are the stations which are waterlogged? We are trying to give that information in terms of how much rainfall is happening. Let's say in our 20 or more rainfall is happening, people say that region gets waterlogged. We are trying to even get this information as well. And after that, it got a huge coverage because it was actually helpful for people, and we realized that a good system actually works if you bring citizen science specifically for the urban region. So this is our team who have actually worked on the urban flooding. Yeah, so that's all from my side. Thank you for your attention, and if there is any question, I'll be happy to answer.
Good afternoon.
Good afternoon.
So, sir, you said the app detects, like we can put our input that I am height of a person, the wall is height, and
Can you please repeat your question? Sorry, I didn't get.
So you mentioned in the app that, like we can put our input that this height person and the water is at this right. I can give my input to the app. So if there are people who are sitting with the app and putting wrong input, are there any background fact checks again before putting it on the app?
It's impossible to perform any kind of quality control. But the idea here is that we believe that people, most of the people will give correct information. So let's say there is an outlet. So let's say if there is a region which is waterlogged, and let's say 50 people say yes, it's waterlogged, and one person says it's not waterlogged. So then it's quite clear that one is essentially the outlier. So the idea here is that this kind of system will only work there are more participants, and we believe that most of the participants are honest. There will be few who may give inadvertently or intentionally wrong information that can be ignored. So that's the way it should work, but we have not used any kind of quality control at this moment. But that's an important thing. Also very difficult to do it at real time.
So, like, will the app in future steps make it quality control and like they could fact check before putting it on? Like if it's only one person.
You can't do that. That's problem, right? You cannot make it real time then. If you are performing an analysis, it will take some time, right?
Yes.
The first part information has to be provided. So we have to rely on people. But what I found is that people don't give random information. Most of the cases, we have not found a single case where there is random information in the last season, which is very interesting.
Yes, sir. Thank you.
People generally want to help people, and this is not associated with any kind of any government agency or anything. It's a completely independent body, and where we say that run by citizens for the citizens. So people are kind of honest. So they don't have any other hidden agenda or anything. So which was actually good. But a quality control is important, but how to make it in real time, it's a big question.
Yes, sir. Thank you, sir.
Good afternoon. Good
Yes.
Afternoon. In the first project where you compared the precipitation pattern of Alibag and Mumbai, you did a PCN cluster analysis. So may I know what are the parameters that you used in PCA and what are the parameters that came on the top that actually controlled the urban precipitation change in Mumbai?
This is not precipitation change. This is for understanding the circulation patterns that results into extreme precipitation over the region. So what we try to do is that we try to cluster FDS weather pattern. Okay. So let's say a specific weather pattern can be given by U wind, D wind, the moisture, the temperature, humidity at different levels, potential height. So consider all of these variables, and they are highly correlated with each other. Just to reduce the dimension, we have done the principal component analysis, and then we perform the clustering with those principal components to understand if we can classify the days based on weather circulation pattern. And if you have classes those days, then you can find out that most of the extreme days belong to one class. That is the so that day's circulation pattern of that class, the circulation pattern associated with that specific class is the extreme circulation pattern. Okay. That's what we have done.
Okay. Majorly the components are not morphology, but just
no. They are the circulation pattern. So we wanted to understand which circulation pattern results into extreme precipitation, and then we are trying to find out that if the extreme precipitation to those circulation pattern are they different in Mumbai, Alibag, or same. If urbanized doesn't play any role, then they have to be same. They are different, and their changes are different because of urbanization.
Okay. And in Mumbai, what are the areas that you did you considered for the analysis? Is there certain areas in Mumbai that you considered for the analysis?
Yes. I have shown that horseshoe pattern. those are the regions which is normally very high rainfall in Mumbai, and those are also the low elevation region because those are around the Sanjay Gandhi National Park, and those are also low elevation region. So they are prone to extreme flooding because of heavy precipitation and low elevation, and also close to the coastal region, of course.
Okay. Thank you, sir.
Thank you.
Good afternoon, sir.
Good afternoon.
Sir, it is a natural tendency of human beings that whenever they settle at a particular place, they do try to expand their territory. And as we are moving forward with time, the urbanization is a necessity and it is a must for human beings. But on the other hand, urbanization is directly and adversely affecting the climate change. So my question is that it is possible to occupy urbanization in such a way that it does become climate friendly.
Yes, that's what we call it now, urban planning. We are not talking about random urban planning nowadays. So whenever there is an urban planning is happening, it should be sustainable. So it should be whether smart and climate ready or climate smart, whether it is whatever term you use, it has to be like that. Otherwise, there will be problem. That's what we are facing. So I mean, most of the existing cities are not climate friendly. That's why there is a lot of pollution, etc. But I hope the new cities will follow certain guidelines or do an extensive study with urban microclimate and so on, so that they will be ready for the climate change. Thank you.
Thank you so much, sir, for joining and giving a very valuable research that you have been doing and sharing it with our students and participants, and also setting the tune for our course for 5 days. Thank you so much for joining.
Thank you. Thank you very much.